Hey guys, I forgot to mention at the end of this video, so I'm going to go ahead and add this to the beginning. I have made a repository with this project. And so you can go ahead and clone that and kind of follow along with the videos. I'm not sure if I'm going to commit everything to main or if perhaps every video will be a different branch. So depending where you catch this series, you can just jump to that branch and it will just keep adding on, something like that. Anyways guys, so the link to the repo will be in the description below.
Hey guys, how's it going? So in this third part of the video, what we're gonna try to do is these things I have outlined here. We may or may not get to everything depending on how long this takes to explain, so I might have to turn this into a part 4 also. Before anything, I wanted to go over something that happened last time. If you recall, I couldn't get the debugger to pause at bootloader main here, even though in the debug configurations I was telling it to pause, set the breakpoint at bootloader main, because usually it starts off and it pauses at regular main. And this wasn't working because, as one of my users pointed out to me right here, that I do have a spelling mistake. So what happened is that here it says bootloader, while here I was telling it to stop at bootloader main, and obviously it couldn't find that. So I'm gonna go ahead and fix that little typo here, and if it exists here, that means it's probably also in the header file. Yep, copy and paste, that's what happens. Okay, and also here in main somewhere. Okay, so that's out of the way. Now this same user actually also had a question. He was wondering why I added the offset of 4. If you go to the ARM, well, right here, you go to the ARM developer website, they have a image here that is of the vector table. As you can see, the reset handler is offset by 4. So whatever the initial address is of your application where your vector table is located, the reset handler is always 4 places above that. So that's why in the bootloader, here it is, I have the user application location, which is this, but I want to jump to the reset handler, and thus this is why I add 4. So that's where the +4 comes from. Okay, now that I have some of that stuff out of the way, we're gonna go ahead and start do some of these things here. The first thing is I want to read and write to Flash. To do that, I suggest that you first get your hands on the HAL manual for your specific chip. You can just Google the series of your microcontroller HAL manual, and it's usually the first PDF that pops up. And in here, I'm looking for the Flash generic driver, which is right here. I open that up to firmware driver API description and programming operations. Yeah, so this is what I'm looking for. These are the functions that I'm going to be using to program the Flash of the microcontroller. Obviously, you also need to get your hands on your data sheet, on your reference manual rather, so that you can know where you're writing to and all that stuff. So right now, just for testing purposes, I'm going to go ahead and write something to sector 6. And I'm going to try to read it on boot up. If it exists, then it'll give me a message of sorts. If it does not exist, then we can go ahead and write it. All right, so let's get that going. So I'm going to go ahead and just make a function here. We'll call this void simple write. And it's gonna, well, I don't really need it to do anything because this is just for testing. I don't need it to take any parameters. Let me go ahead and copy that from my previous project here. Okay, let me clean that up for you guys. Okay, the first thing that's needed, for starters, I don't need a for loop. I just want to write 1 byte in there. But the important bits here are these right here. The first thing you're gonna need to do is to unlock your flash. This allows you to actually write to your flash. And ooh, this is not unlocked. This is locked. And you need to, at the end, once you're done, you need to lock it so that you don't have any accidental writes or erases for that matter. The main function that we're worried about right here, we don't need this either, is this HAL flash program. This function is the one that does the actual writing. And as you can see, it takes three parameters right here, and we'll see what they are. So the first one is type program. This says it indicates the way to program at a specified address. This can be a value flash program type. Okay, then that will probably be in the header, but we can find it down here too, where it says if program type equals flash type program half word. So let's click on that. And these are the 3 or 4 different program types. You can write in bytes, half words, words, or doubles, and that will obviously coincide with whatever is in your data sheet, where it tells us that we can write in byte, in half word, in word, and in double. So that is basically what that parameter is telling us, that we're telling the microcontroller what kind of write operation is this, how much data are we writing. Okay, so if we go back, the next is the start address. So here you would give it the start address and then the actual data. So let's go ahead and do that. Here I've dereferenced a pointer of sorts, which I'm not going to do. Actually, let's delete that. I'm going to just write a constant. Let's declare it up here. Let's just call it hex word or something like that. Okay, so I am going to write the hex value dead beef. So that's what I'm going to write. So I'm going to have that as my actual value that I'm going to write. And I'm going to write it in word. So it's going to be a 32-bit word. That's the word size of the microcontrollers. And the address, I'm going to go ahead and write let's write it at sector 6. So what I'm going to do is make a define over here. Let's just call this sector 6 equals that. Okay, so I'm just going to write to this address here. Where did it go? Here it is. Okay. And that's that. Oops. My scrolling is being funny. Okay, so that's a simple write HAL sort of flash write operation. The next thing that I want to do is just write a simple a pointer so that I can read from this address. So we can say this is an unsigned integer 32 pointer. And this, the only purpose this is going to serve is so that I can verify that I have, let's call this my hex word, is so that I can verify that I actually wrote the data that I'm hoping that I can write, and that it will persist across a power cycle. Pointer, and it's going to point to this, to sector 6. So this is just a 32-bit pointer to this sector 6, and we should be able to read back the word. So at this current time, I don't want to jump to the user application, so I'll probably comment that out. Actually, nah, we can just keep the print just so it doesn't crash on us. Okay, so what I'm going to do here is I'm going to go ahead and I'm going to write this. I'm going to call this function. Well, first let's just make a little prototype of it up here. I'm going to go ahead and call this simple write function. Okay.
So yeah, let's do that, and so that I can show you that well, what it does basically. So let's just let me plug in my microcontroller before anything. Okay, so let's run and debug this. Let me close this. Okay, I'm gonna stop right here. And right now what I'm going to do is I'm going to open up the memory viewer, and hopefully we can see that write operation. Okay, so here I am at the simple write function. I'm going to open up the memory viewer. We're going to add that sector 6 address. And as you can see, okay, well, it already exists there. And that's because obviously I was trying this before in a different application. So I'm gonna actually, just to make this sort of a more full demonstration, let's erase the entire chip. Okay, the entire chip is now erased. So if we go to address 8 with the 4 right there, and there's nothing there. All right, so let's give it another shot. So now we'll go ahead and debug. Okay, we'll run to the simple write. There it is. We'll look at our memory viewer again, hexadecimal. There you go. This time it's actually empty. So now I'm going to step over the function. And now there it is, dead beef. Obviously it's written in little endian, but it's there. Okay, so now I want to stop this operation. I'm going to unplug my microcontroller. Okay, so the microcontroller is unplugged. What I'm going to do is remove this simple write operation, and let's just pause the code right here. Actually, what I was going to do, I was going to read it with this. Well, let's just read it then. Print. Let's see. If my hex word is equal to 0x dead beef. Okay. On the beef, I guess. Else found no beef. Okay, so now let's just run this, and instead of pausing there, we'll just pause right here, and we'll see what it prints out. Oh, I gotta plug it in again. All right. So the idea here is just simply to demonstrate that the value persisted across a power cycle. Oh, I have to open up my viewer. Show view terminal. Oh, there it is. Okay. It is paused up here, so let's run it. Well, let me clear this thing actually. I have to first connect to my COM port. Okay, there it is. And play. And play again. Found the beef. Okay, so it found the beef. That means it found this value at that address, which again, we can go back and we can look at it, and it's still there. So it persisted through a power cycle. Okay, so that's basically just proving that yes, we can write to flash and it will persist through a power cycle. Like I mentioned in the first video, you definitely have to look into your microcontroller and see if your microcontroller is arranged in terms of sectors or pages. That being said, one of the first things that I do want to do is to write a erase function to erase a sector. So I'm going to go ahead and copy that from, obviously, from my previous application. And it lives, and it's going to look like this. And I'm going to copy it with the comments and everything. For now, let me delete this simple write, because we don't really need that. We could get rid of this stuff. This is, I guess this is okay for now. Okay, so the simple right, I'm gonna start building my application here at the bottom. Okay, so this is a simple erase sort of thing, and as you can see, all it does is it makes this type. It makes an instance of this sort of struct, and you're giving it the how many sectors you're going to erase. You give it basically the starting sector and a voltage range, and make sure that there's no errors, or I didn't even use it. But and then you're gonna unlock the flash, and you're gonna call this flash erase function. Now, what does all this stuff mean? All right, so if we click on this struct right here, again, that's gonna take us to the header file for this stuff, and these are the elements that this struct has. First is the type of erase. Is this a mass erase or it's a flash type erase or sector erase? I'm sorry. So we can go ahead and go to that, and we can press copy, control find. All right, so these are the types of erases that it has, sector erase or mass erase. I actually didn't even add it here, which I should have for the sake of clarity, because as you can see, it's 0 and the default is 0, so that's why, but we should add it. Oops. Type of erase equals that. So this is the type of erase it is. Obviously, number of sectors is just that. It's number of sectors. The next one is banks. We're not concerned with banks right now. If this is dual bank or not, we would be. And then the actual sector that you're starting at. So if let's say if you're erasing 3 sectors, or you wanted to erase everything from here forward, you would tell it to start at sector 4, and then you would specify a number of sectors to be 4, and it would erase all of these right here. So I gave it to just erase sector 5 because that's where my user application is going to live, thus this address that we used before. And I know for a fact that my user application is not larger than 128 kilobytes, so that's why I'm only erasing 1 sector. Obviously, your application could be different. If you're using like an F103 and your sector or pages, I don't recall, are only 1K, then obviously your application will probably be larger than 1K. So then you'll have to erase more pages or sectors. And then the next thing is this voltage range thing, where you can actually find this information somewhere. So let's copy that, control F, find, and here it is. And this header file actually tells you, given your device, what to use. So obviously I'm operating my device between 2 and 3.6 volts. It's operating at 3.3 actually, so then that falls in that range. There is no external VPP. I'm not sure what this really means. If there's like an offset or something like that, you would probably use that. But since my device is operating just kind of how most people will probably be operating it, I did choose this voltage 3 range. And so that's that. Your flash erase function needs a place to store an error code if there's an error. Here I did not check for my errors. Obviously we can add a little to do here, because if you want to make this a robust bootloader, every function that returns something, we need to check the return. Return of flash erase and handle it. Okay, so that's something to do. Another thing that I listed as a to do here is to abstract the sector erasing based on app memory location and size. So when I'm bootloading an application, you don't know beforehand how large that application is going to be. So I can't hard code 1 sector right here. I should not be doing that. I should be getting a frame packet from the desktop application or whatever is sending me the new firmware. It should send me a header that tells me, hey, this application, it's actually, X amount of kilobytes. And then based on that, I need to calculate how many sectors or pages I should erase. If you hard coded and one day, you doing more and more updates, and then the new firmware is larger than whatever you hard coded in the bootloader, then you're in trouble. So that's definitely something that needs to be handled differently. It's a to-do right now, so for now I'm just erasing one sector. Okay guys, I think I'm gonna cut it short. Not really short, it's already 20 minutes, but that is enough of some minor things that I want to show you. And then in the next video we can actually go ahead and start writing our frames.h file, which is going to dictate how our microcontroller is going to communicate with the host application sending us the firmware, and it's all going to be based on frames and things like that. And then we'll start writing this frames.h, and we'll hopefully make a function to send a frame and assemble a frame and disassemble a frame. And once we start doing that, you can kind of get a more clear idea of how this entire bootloader is going to work. Alright guys, thank you and stay tuned.